Hello everyone, it's Mrs. Hanson here. We're beginning our journey together in our class looking at thermochemistry, the first module in lesson 1, with our learning goals of defining energy and distinguishing types of energy, describing the nature of energy changes and that accompany those chemical and physical changes. We're going to be able to distinguish the related properties of heat, thermal energy, and of temperature. We'll define and distinguish specific heat and heat capacity and describe the physical implications of both. And finally, in our first section of thermochemistry, we'll practice performing those calculations involving heat, specific heat, and temperature change. In this beginning part of our video, we'll talk about energy. Let's begin. So we'll begin by simply defining the term energy, and in your notepad at the top it says, what is energy? And I'd like you to simply write energy, a classical definition here, is the capacity to do work. Energy comes in two different forms. If energy is the capacity to do work, we look at two classes of energy, what we call potential energy and what we call kinetic energy. I'd like you to define potential energy as the energy that is stored. The energy of position is another way to define that. Now in chemistry, potential energy is that energy that's stored within a chemical bond. And when we break bonds, and that's what chemistry is all about, energy is released. A second category is known as kinetic energy, and I'd like you to define that as saying it's the energy of motion. Anything moving possesses kinetic energy. We call this the law of conservation of energy, which is a law in thermodynamics. It simply states we cannot change the amount of energy in the universe. We cannot create it. We cannot destroy it. All we can do is let it change from one form to another. The law of conservation of energy says the total energy in a system does not change. Energy is conserved. Energy can change from one form to another. But the amount of the energy in the universe is constant. So a great example of potential energy, and I know this is archery, which is coming up in the Summer Olympics, pulling back that arrow, pulling back the string on the bow and having the arrow ready to launch. When that position is as far back as that lady can possibly pull, she's got potential energy stored in that bow. And of course, when she releases that, you have that now in motion, all of this stored energy in this particular, the string being pulled back is then released and the arrow goes forward. So stored or position, and then of course the motion creates kinetic energy. And I like this diagram too. Here we are at the very top of a roller coaster hill. So 100% is stored energy, the energy of position, gravitational energy here. And then of course you start to go down the hill. About halfway, you have half kinetic energy, half potential energy. And at the very bottom of the hill, 100% kinetic energy because there's no energy of position any longer. So at the top of the hill, stored energy, and when you're in motion, kinetic energy. And when you think about this law of thermodynamics saying we cannot create nor destroy the amount of energy in the universe, we only allow it to change from one form to another. These are examples of those types of energy. Potential energy in chemistry is the energy stored in bonds. Kinetic energy in chemistry is stored in bonds. Kinetic energy in chemistry is thermal energy, the energy of moving particles, such as heat flow from a hot object to a cold object. There are other types of potential energy, such as elastic. Remember that bow that we talked about in the previous slide? When she pulled back the string, she was storing energy due to tension. There's other types, such as nuclear. You blast apart a nucleus of an atom, all kinds of energy is released. or gravitational potential energy, like at the top of the hill in the roller coaster. Kinetic energy includes thermal, mechanical, electrical, sound, and electromagnetic waves. All of those on the EM stands for electromagnetic spectrum. All of those are in motion. So if we're studying energy, specifically in chemistry, it will be stored in bonds or released or absorbed as heat. So our focus, of course, is chemical bonds. Chemical bonds store potential energy. And a compound with lower potential energy is more stable than a compound with higher potential energy. That is just really a natural law. It says compounds want to be at the lowest energy possible. And I think about the natural state. I think all of us want to be at the lowest energy level possible, especially with our 8 a.m. chemistry class. Then we see that reactions that form products having lower potential energy than reactants, they're actually favored. So what that means just visually, here's energy on the, and just kind of draw this with me if you will on your margin. Here we have just an XY axis where we can see on the Y axis is energy. And we'll learn that energy is going to be measured in joules or in calories. Calories might be a more familiar term just from food intake is measured in calories. And in the metric system, we'll write down joules. But you can see as energy is increasing on the y-axis, and you can just think of this as time. Time goes by and reactants turn to products. You call that progress of a reaction. If the reactants have this, just kind of an arbitrary line that I draw, a starting amount of energy, and we'll learn that there's this little energy barrier that separates reactants and products. We'll learn that this is called activation energy. And again, we'll redraw this several times because we'll have this energy barrier that here I'm going to abbreviate EA as the activation energy. And as time goes by, the reactants turn to products. And you can see then there's a difference in the amount of heat content, the amount of energy between the reactants and products. The reactants are of higher energy than the products are down here. And we'll see that heat is released. And this is a more stable configuration because they are of lower products. We will learn that this will be called exothermic, heat releasing. And when bonds break and new bonds form, heat is being released, energy is being released, and we'll measure that energy using bond dissociations. So these units of energy I've been saying, one is known as a calorie, and you can abbreviate that with a small c, or some people will write out CAL for calorie. We define that to be the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. So a small case calorie, how much energy needed to raise 1 gram of water 1 degree Celsius? That is also known as the specific heat of water. And you should know that the specific heat, we'll learn, is a kind of a definition for this. And it just says the specific heat of water, you can say, is 1 calorie. It takes 1 calorie to raise 1 gram of water by 1 Celsius degree. And so in the metric system, there is another unit of energy. Now in America, we're used to the English system carrying calories of energy, but we should also be familiar with the metric system. The unit of heat energy is known as the joule. And this is actually an honorary name from a physicist whose last name was Joule. So you'll see that was a capital J when we write out its unit. A joule is another unit of energy. So you could say the specific heat of water in a joule is 4.184. That's the conversion between a calorie and a joule. It takes 4.184 joules of heat energy to raise 1 gram of water by 1 Celsius degree. The equivalent values between calories and joules should be memorized. You'll need to know those conversions, so I'll just encourage you to remember 1 calorie is equivalent to 4.184 joules. So both joules and calories can be reported in larger units. So these are actually kind of small calibrations. When I say 1 calorie, it's kind of a small number. So joules and calories are more often reported out in kJs, kilojoules, and kilocalories, kcals. So just thinking that through, we know that kilo means 1,000. So it takes 1,000 joules to equate to 1 kilojoule. It takes 1,000 calories to equate to 1 kcal, a kilocalorie. And so we can equate these two as well. A kilojoule and a kilocalorie would have the same conversion as a calorie to joule. 1 kcal is equivalent to 4.18 kilojoules, kJs. So let's kind of bring that out to practice. Let's practice converting between heat units. You'll need a calculator for this part of your lesson. Perhaps pause your video if you've not yet grabbed your calculator, or perhaps you're used to having a calculator every time we start with chemistry. But this is the bottom of page 1 where it says, let's practice converting between heat units. And I pulled this right out of your text. A reaction releases 421 kJs of energy. How many kilocalories does this correspond to? So we're working to memorize our conversion that we equate 4.184 kilojoules is the same as saying 1 kilocalorie. So let's begin by writing what was given to us, 421 kJs. Now remember, our conversion, what is it that we want over given so that our unit will cancel? We were given a kilojoule. I want to make sure it cancels, so it must go on the bottom. And I want to end with a kilocalorie, so it needs to go on the top. So we end with it. Our conversion says 1 kilocalorie is equivalent to 4.184 kilojoules. So this looks like a divide by problem. And let me pull my calculator out. Let's hit this together. I have 421 divided by 4.184. And my screen reads 100.621 and it goes on and on and on. Let's consider sig figs. I have 3 sig figs here. So my answer should also have 3 sig figs. So I'll round to 101 kilocalories. That's not too bad, is it? Let me ask you to try some on your own. Please pause the video, work to create mastery, right? So the more you practice on your own, the more proficient you become. You're turning the page in your notepad to the top of page 2. Come back to the video when you're ready to check your answers. Pause, work ahead, and then come back. That's me turning the page. In letter A, we started with 42 joules, and we wanted to go to calories. Remember what we want over given for our conversion. We want to switch to calories, and we were given a joule. We know that our equivalent values, 4.184 joules, is the same as saying 1 calorie. So you divided. You said 42 divided by 4.184, and you found 10, and your screen said 10.038. But remember, we're considering sig figs, so I'm going to write 10 with a decimal point to make sure that's 2 sig figs, and my unit there is calories. 55.6 kcals, 2 calories. So what is it that we want? we want a calorie given a kcal down below. Whoops. So I think about want over given. It takes 1,000 calories to equate to 1 kcal. So we're moving our decimal place 3 spots over. So when I write that out, 55600. Now I think about sig figs. This is the number of calories. I'm only allowed 3 sig figs in my final answer. And right now I have ambiguous zeros. So if I don't leave as, no decimal point, because I don't want those zeros to be significant, I'll still have only 3 sig figs. So 55600 with no decimal point gives me the correct magnitude of the number and still 3 sig figs. I did place a decimal point here to ensure I had 2 sig figs, so that one was needed. I'm kind of reviewing our sig fig rules. 326 kcals to kjoules. So here I want my kilojoule and I need to cancel the kcals. 4.184 is our conversion between the land of kilocalories to kilojoules. So 326 times 4.184, and we get a value that says 1363.984. We need 3 sig figs. So this fourth number here is looked at, and it is not up high enough to round. So 1360, that's 3 sig figs with no decimal, kilojoules. Letter D, 25.6 kcals times, let's see, we want joules. I need to go, so this is a good one. We need actually 2 conversions, don't we? Because our conversion says a kcal to a kj, I can get there. And so I have to give myself a little more room. So let me just rewrite that answer. Yeah, this will work for us. We want kcals. And so therefore, to cancel kcals, it takes 1 and 4.184 kjs, and I can easily convert from a kj to a j. And by doing that, we know it takes 1,000 joules to equate to a kilojoule. So this involved 2 transfers. Kcals canceled in the first step, kjs canceled in the next step, and we'll finally land to joules. So to hit that 25.6 times 4.184 times 1,000. And my screen has a really big number. It says 107110.4 joules. We have to equate that to 3 sig figs. There's 3 there. So 3 sig figs, 107000, no decimal. And that way I'll have 3 sig figs in my final answer. So I have the correct magnitude, the size of the number is correct, and I have 3 sig figs reported. Good work. There's some more.